Okay, everyone, I think we're going to get started. So if anyone downloaded the PowerPoint slides last night or first thing this morning, I made a last-minute change to the material, so you may want to re-download it off the T-Square site. The reason being that I decided I wanted to cover current exchangers in the last portion of this class. I'm not going to be testing you on this material because I usually devote an entire lecture to current exchangers. But I think it's really fascinating stuff, and it's an important principle that I want you to at least be exposed to in biotransport. So we're just going to devote a little bit of time at the end of the class. I cut out an example problem that we were going to work through on the Chilton-Colburn analogy so that we had time to talk a little bit about this. All right? So some 3,300 numbers. By this point in the class, you're bogged down with all these different abbreviations. We've got Reynolds number, Sherwood number, Schmidt number, Lewis number, which we haven't talked about yet, Prandtl number, Peckley number. We're going to introduce the Stanton number today and the Nusselt number. So all of these, of course, have their own two-letter abbreviations. And they're really all pi groups. And when we discussed pi groups in the first third of this class, we discussed them with respect to similitude and the ability to scale things, right? So you don't just scale things by length dimensions alone. You have to scale them by the pi group in order for things to be equivalent. And so, of course, one pi group that we've been discussing a lot in this class is Reynolds number. And when you go out in the world and you talk about fluids, Reynolds number really is the currency that people use to basically say something's laminar or turbulent. And they expect, when they throw out a Reynolds number, for you to have a basic understanding of what that means in terms of the balance between velocity, dimensions of interest, and fluid viscosity. Okay, so this Reynolds number then has been really key in all these other things that we've been doing in the class. So when we talked about mass transfer, we discussed the Sherwood number, and the Sherwood number as a way of coming up with either solving for this elusive Kc, or really K sub f, depending on whose notes you're looking at, value, which is really hard to determine experimentally, that convective mass transfer coefficient. So it's a way of calculating that value. And remember, we talked about using this to solve for also that average KF, which is going to be evaluated across a scale of interest, like a flat plane, for example. So we have the local value and that integrated value that we could calculate. So that Sherwood number is really important for that. Also with mass transfer, we talked about the Schmidt number. The Schmidt number being a balance between momentum diffusivity and mass diffusivity, or molecular diffusivity. Okay, and we said depending on if it's greater than 1 or less than 1, it said something about the overall contributions of momentum versus diffusion in a system. So it turns out that there is a relation that can look at thermal diffusivity versus molecular diffusivity, and this is the Lewis number. This is something we have not talked about in class, but it's out there, and so I just thought I'd mention that this is another ratio that you can consider when you're looking at what's dominating in a particular system. Now, the Prandtl number is our equivalent of the Schmidt number, only for heat transfer. And the Prandtl number is then looking at momentum diffusivity versus thermal diffusivity, if you will. Our Peclet number was defined in the mass transfer section as being the product of the Reynolds number and the Schmidt number. By analogy, sometimes people use the Peclet number for thermal transfer. So you could have the Reynolds number times the Prandtl number and also get a Peclet number, right? So this could be also equal to, for heat, we could have a RE times PR equaling a PE. Okay, so for some reason, one guy got the credit for both, whereas the others, there's always a new name associated with it. Okay, today we're going to be talking about the Stanton number. And the Stanton number is going to be evaluated in terms of either convective mass transfer versus our fluid kinematic viscosity, or it's going to be evaluated in terms of our convective heat transfer coefficient versus our kinematic viscosity. Okay, so this is sort of like looking at the equivalent would be like the Schmidt number or the Prandtl number, only this is really for convection, where these two are conduction. Sorry, my style isn't lining up with the columns here. Okay. So it's looking at a different feature of heat or mass transfer versus that kinematic viscosity. And finally, we have the Nusselt number, which is equivalent to the Sherwood number, only for heat transfer. So this is like our SH, in that we can solve for an H bar, or we can solve for a local H, depending on whether we're evaluating it across a distance or at a specific location. Okay. So as I was putting together this lecture on analogies, I came across, if you put in transport analogies in Google, a PDF from UCSD pops up. And this person, this lecturer in their engineering school, had a chart, and I didn't use it verbatim, but I thought there were some nice analogies on there that I wanted to present to you guys, because at this point in the class, we're starting to relate momentum to mass to heat. Okay, and so at this point, we've got different entities which we're evaluating. We're looking at concentration, or we're looking at temperature, or we can even think about this in terms of our momentum in the system. And we can look at the diffusion of these phenomenon propagating through a fluid environment. So we can think about this as a transport diffusivity in terms of our kinematic viscosity. We can think about it in terms of our diffusion coefficient, or we can think about it in terms of this alpha value, which is our thermal diffusivity. And remember that thermal diffusivity is slightly different than thermal conductance, whereas with mass transfer, D is one and the same for both. Our transport pi groups, this is just repeating what was on the last chart, only now aligning it in terms of the transport phenomenon of interest. So we've got our Reynolds number versus our Schmidt number versus our Prandtl number. And these really become sort of physical properties of the fluid. Some of these will, these Schmidt and Prandtl numbers can potentially change depending on your system. So we know our diffusion coefficient can change as a function of temperature, for example. Our Prandtl number, it's possible that could change in terms of a change in density, for example. But more or less, we can look these things up on charts. We have other pi groups of interest, like the Sherwood number and the Nusselt number for mass and heat. And then we have a number of transport laws that we can start relating. So we talked about flux, and flux can be considered in terms of conduction here or convection, right? And our 1D transport law of interest for momentum was really relating our shear at a surface in terms of that partial derivative with respect to y for our velocity. And Newton's law for Newtonian fluids stated that we had a minus mu times dvx by dy for our shear stress. Other relations to consider. Our Laplacian shows up in terms of, this is a very simplified version of Navier-Stokes. This is Stokes flow, where we're considering just an instantaneous change in velocity being a function of our pressure gradient. We also had the Laplacian show up in our fixed second law and our energy equation. Okay, so this bottom graph here then is just showing how if we have a boundary layer, we've got a V infinity, a T infinity, and a C infinity that we're considering averaged in that fluid stream that's then going to hit a plane. And as that boundary layer develops, we've got a thickness associated with each transport phenomenon. We like to evaluate these when they're equivalent because that's super easy. That's when your Schmidt number equals 1 or your Prandtl number equals 1, but that's not always the case. And so we can think about these relationships between our delta values and the thickness associated with these based on properties of our system and evaluate when those are in different thicknesses. And that's one thing we're going to talk about today. One other thing I wanted to mention is that this is from Dr. Ethier's notes, is that we also have these electrical analogies we've been able to use for mass transfer and heat transfer in terms of thinking about resistances in series and allowing us to look at composite situations for either diffusion of molecular diffusion or heat transfer. Okay, so if we want to relate those boundary layer things together, we have to consider some circumstances here. If we're going to do this correctly, we have to assume that no energy or mass is produced within the system, which is saying that we have no R sub A term for mass, or we have no of those Q dot terms that I mentioned for the energy equation. So that means there's nothing added into that Reynolds transport theorem that's allowing for accumulation or removal of mass or energy from our control volume. That's allowing us to say that everything that's moving into this space of interest is happening through basically our convection or our diffusion. That's it. We're going to ignore radiation because we said that's a special case. And remember with that island analogy, we said that's like someone flying in with a helicopter and dropping off people instead of them arriving by boat or by bus. Right? So that's a special case. We're going to ignore that here. No viscous heat generation, so we're not going to let any kind of energy transfer occur by the fluid acting on the system. We talked about how there are different types of work that had to be balanced in our control volume once we considered shaft work and things like shear or viscous work. We're going to say that the velocity profile is not affected by mass transfer. So far we've really ignored the fact that when you have very large concentration gradients, then you can have sort of this convective tumbling that occurs based on just the molecular distribution alone. We're ignoring that in the system altogether. And then we're going to say these physical properties like density and D and things like that are going to be constant. So Reynolds, being that brilliant person for all transport, came up with an analogy. in which he suspected that transfer of momentum and energy were identical. And so if that's the case, if they're totally identical, we're going to say that Prandtl number is equal to 1, which means our balance between momentum diffusivity and heat diffusivity are identical. And if that's the case, then for this Prandtl number equal to 1, remember, whenever we've considered this momentum boundary layer, we've always considered some fluid stream in which we have V infinity here, and we're evaluating our V sub x at different locations in the vertical direction, right? And this V sub x changes as a function of y. So we always normalize that Vx by V infinity for our momentum boundary layer. And then for the equivalent with temperature, we always normalize that with respect to an unaccomplished temperature change. So this is a different way of normalizing things. So in both cases, we're going from 0 to 1. We're just adjusting our variable so that it scales easily. And that scale is always going to be equivalent. Because our Prandtl number equals mu Cp over K, we can plug in, we're saying that this Prandtl number is equal to 1, which means we can multiply through by 1 on either side. So if we have a multiplying by 1 on this side, we can move this K over to this side, and now we've got a mu Cp on one side and a K on the other side. Okay? So we're just manipulating the fact that we're saying that this partial derivative for the momentum boundary layer is going to equal to that partial derivative for our thermal boundary layer. Okay, so starting with that same equation on the top then, we're just going to rearrange the terms. And remember, we're always evaluating this partial derivative at the surface, at y equals 0. That's our no-slip condition there. And we're then going to say that we're pulling out the V infinity from our partial derivative because we're saying, okay, that V infinity doesn't change with y. And the only thing that's changing with y in that partial derivative is V sub x. So we're pulling out that V infinity. And we can also do the same thing for our denominator here, because we're saying this is our total gradient or our total differential of t in our system. So we're saying that, again, if you draw that boundary layer, we've got T infinity out here, and we have some Ts at the surface, and we have that heat flow coming out of that surface. We're saying that this versus this is always going to be the same at every y. It's just a fixed difference. And so that fixed difference can be pulled out as the derivative. And then the only thing changing as a function of y is this t. I should write a t here, not an arrow like b. A t at a particular location, which can change as a function of y. So that really should be evaluated like that. Okay. So if we look at what this is, it turns out that this, when we were deriving our Nusselt value, we were using something like this, and it turns out that this whole chunk right here is equivalent to our convective heat transfer coefficient, which allows us then on the right-hand side to stick in H, and on the left-hand side have something that's a function of mu Cp over V infinity. Okay, so if you think way back to the beginning section of the class, when we were talking about local shear stress, we used a term called C sub F, which was that skin friction coefficient. And Dr. Ethier came up with a relationship where we could say more or less we can approximate this skin friction coefficient as tau divided by a 1/2 rho V infinity squared. Okay, so if you go back to, I think it's like Unit 3, you'll find this relationship somewhere in the notes. So, and because, as I was mentioning earlier, that tau term, our shear stress at the wall for Newtonian fluids, is equivalent to our mu dV dy at y equals 0, then we can approximate this by substituting in for our tau this expression here, so that our C sub f is equal to mu over 1/2 rho v infinity squared times dv dx dy evaluated at y equals 0. Why on earth would we want to make the skin friction coefficient more complicated, right? The reason we're doing that is because we're coming up with a relationship that allows us to think about this in terms of our heat transfer. So we're going to use what was on the previous slide in this new form of the skin friction coefficient to essentially equate the two. And this is how we come up with the Stanton number that I mentioned on that first chart. We're coming up with a relationship where it's dimensionless. It relates convective heat transfer to momentum transfer. And it allows us to say that our convective heat transfer coefficient divided by rho v infinity Cp is equal to our skin friction coefficient divided by 2. So this is really powerful because that skin friction coefficient was telling us something about the effective resistance that the wall was putting on the fluid movement. And here we've essentially got a new relationship where we're thinking about heat transfer in terms of that momentum resistance, if you will. So this particular equation holds true when the Prandtl number equals 1 and there's no form drag. So we're only going to be thinking about pipe flow or planar surfaces, the way we thought about our Nusselt and Sherwood numbers. So we can go through this exact same analysis for mass transfer. And again, why would we want to do this? Well, once we have a way of relating momentum to heat to mass, then it's really easy to swap them out and use knowledge about one to analyze a situation for another. So just to go through this, first of all, I should finish what was happening for heat here. So the Chilton-Colburn relationship took what Reynolds did and said, it's very rare that you have these things totally equivalent to one another. So while it's nice to consider our momentum and our heat transfer boundary layers to be the same thickness, usually they're not. And so if we think about a Prandtl number not equal to 1, then there's a more generalized form we can use where we multiply our Stanton number by Prandtl to the 2/3 power. And that then becomes equal to our skin friction coefficient. And so this is known as JH. It's like the J factor for heat transfer. And that's how we're going to then relate heat to momentum. Okay? So let's just quickly look at how you would do this for mass transfer. Going through the exact same derivation, only now substituting in the Schmidt number for the Prandtl number. Reynolds could go through and look at that unrealized concentration change and equate that to the partial derivative at the wall of the velocity, the normalized velocity, and go through the same analysis. So now instead of our H, we've got some K sub C. I apologize. I keep trying to correct this in the notes because we've learned it as K sub F this semester in the class to be consistent with Dr. Ethier. So then we have a new relationship which considers the skin friction coefficient over 2 to be equal to our Kf over that kinematic, that velocity v infinity. And that's then relating convective mass transfer to momentum transfer. And again, this is for the Schmidt number equal to 1. And then the Chilton and Colburn created a variant for the non-ideal condition where now our JD for diffusion is going to be multiplied by our Schmidt number to the 2/3 power, just the way the Prandtl number was stuck in there. So now this is beautiful because now we can say the complete analogy is saying that our JH equals our JD equals our skin friction coefficient. All three forms of transport in a single expression. And so you will see this written in different ways because there are forms that this can take in terms of whether you evaluate it in terms of the Reynolds number or you have it in an expanded form or not. So if there's form drag present, these two will still be equal, but they will not be equivalent to the skin friction coefficient over 2. So you can always have a JH and JD equal, but it's when you've got that special geometry that you can relate all three together. Okay, so just to write this out in different forms, you can think about this in terms of the Stanton number. And remember that Stanton number will be calculated differently based on whether you're talking about heat or mass. But you can write it in this collapsed form. You can think about that, that ugly heat transfer expression in terms of the Nusselt number over the Reynolds number. That's another way of evaluating it. But all three of these are equivalent to one another. And this is really beautiful. It holds for many geometries. It's valid for a range of Schmidt numbers and a range of Prandtl numbers. So again, coming back to what's the usefulness of this. In last class, I mentioned how oftentimes it's easier to measure temperature instead of a concentration. In a system, we've got great ways of monitoring heat transfer through different thermistors and electrodes and so forth, that you have to have more specialized measurements to do an equivalent of concentration. So oftentimes people use heat transfer as an analogous situation to mass transfer in order to calculate the way molecular movement would be occurring in a system. It's also easier to measure, to calculate the skin friction coefficient than to do either convective heat or convective mass transfer. So if you know what C sub F is, that helps you out with the other unknowns. But then I was thinking about an example from my own lab where it would actually be easier to visualize molecular transfer than it would to visualize heat transfer. So I thought I would just show you this. Because I had shown you this earlier in the semester where we've got these cell traps. And we can apply waves of stimulus to the cells hanging out in these little cups here. And it turns out that several years ago, one of my graduate students developed this chemical wave generator where you've got all of these little cell traps lined up in chambers right here. And so she can monitor these cells over time in her field of view of the microscope, and then she can create oscillations or chemical waves on chip in her microfluidic device by just changing the pressure-driven flow between two different buffers. And she actually colored the buffers with just some nice dyes so that we've got red and blue. You could do this with food coloring. And then we can actually monitor these properties of laminar flow and the very predictable fluid movement that will take place in order to see where this buffer is being delivered when. So if I was to pull this up and just show you how this is. It's going to take a minute. But you're going to start seeing this wave going across. So here are her chambers. And she's monitoring the change from blue to red as she's just altering the pressure gradient between those two valves to allow the flow to come through. Is it going? There we go. Now she's got her wave going. So you see it marching across laterally here. These little lines along here are actually pressure drop channels. So why would she want to add in these pressure drop channels when what she's interested in is the chambers here? Does anyone have any idea? So if you think about resistance, right, we talked about how in mass and heat transfer we think about resistance in terms of series, right? But with volumetric flow rate, we oftentimes want to put resistance in parallel in order to control the effective cross-section and the pressure drop that's occurring on the chip. So this is actually a way of adding resistance so that she can do her manipulation of her valves and not have it jiggle really rapidly. She has a lot more control over it by having that additional thing in parallel here. Okay, so as she's going across here, what we've got is essentially a way of monitoring molecular mass transfer. If these two colored solutions contain concentrations of different values, right? But say what she wants to do in these chambers is to evaluate heat shock response, right? So maybe the pink buffer is at 90 degrees and the blue buffer is at 5 degrees Celsius. Okay, so she would either have to have a special infrared camera or some thermal imaging technique on her microscope in order to visualize that. Instead, she can monitor the molecular movement. She can monitor the molecular movement just colorimetrically, right? And see if there's any diffusion occurring, she'll know it because the colors will start to blend. And she knows exactly where that temperature is taking place because she could use the analogy between mass transfer and heat transfer to calculate what's happening temperature-wise in her system. Okay, so that's an example, sort of a real-world example from my lab on how you might use that. I found an example in the literature for DNA hybridization. So again, if you're looking at this on chip, you'd want to use capillary flow and actually do all of your hybridization by microspheres. So that would be much, much faster than doing something like a DNA microarray where you're on this sort of planar chip with spots that are allowing those reactions to occur. So this particular example in analytical chemistry was trying to evaluate what was happening on this. So if they want to know what the reaction kinetics are within the microfluidic device, where they've got these microspheres with their different DNA probes, and they want to know the rate at which this binding reaction is taking place, they're first going to relate flow rate to pressure drop. Okay, that's something we can do. We know how to make those relationships happen. They use that to convert a relation between friction coefficient and Reynolds number. Okay, we know how to do that as well. They then use the Chilton-Colburn analogy to find their convective mass transfer coefficient based on the skin friction coefficient. So they're starting with pressure drop. They're getting a flow rate from that. They're using the flow rate to calculate the Reynolds number. They're using the Reynolds number to find the skin friction coefficient. They're using that skin friction coefficient to calculate their convective mass transfer coefficient. And then from there, they can establish the concentration profile and then determine the reaction kinetics. Okay, I think this is a really nice example because it shows how oftentimes we don't just have that beautiful variable or coefficient given to us like in a problem statement on a test. And instead, we have to go through a very convoluted way to get to that piece of information we're interested in. But through these analogies, we can make that possible. And so one thing they said in their discussion, which I thought was really nice, is that they said the estimated hybridization reaction efficiency based on that Reynolds skin friction coefficient relation derived from experimental measurements of the pressure loss dependence on the volumetric flow rate and the Chilton-Colburn analogy predicted the experimental data quite well. And therefore, we can use this to predict other chemical reactions occurring at solid-liquid interfaces in many useful applications. So essentially what they're saying is, hey, we were able to make all these measurements, compare it to these theoretical calculations, and it turns out that that's a really, really good approximation for what's going on. Okay, so as I mentioned at the beginning of the class, rather than going through a Chilton-Colburn example, which is actually in your textbook in one of the chapters for assigned reading, I thought instead what I would do is just present a concept for biotransport in the last few minutes of this class, because I think it's interesting and it's a very useful one that you never know when you might need this, this concept in your own careers. So we're going to look at current exchangers with respect to hemodialysis. So hemodialysis is a long-standing quality of life issue for a number of people. It's extended the ability to carry on normal day-to-day activities for people with kidney loss. But as a consequence, the people with malfunctioning kidneys or lack of kidneys are essentially reliant on going to a dialysis center multiple days a week in order to have their blood cleared of the toxin accumulation that would normally be removed by their kidneys. And so a real goal of hemodialysis then is to minimize the time that these people have to sit hooked up to a unit, a dialysis unit. So the more effective your transfer is, the less time this person has to be hooked up to a machine. So what are some of the design parameters we can control? We can control flow rates of blood that are being removed from the patient, going through circulation and being put back into the patient. The equivalent buffer that we'll be using from the dialysis unit is called dialysate. We can control total membrane exchange area, surface area at which this transfer can take place, the length of the exchange unit, the concentration gradient, the transmembrane pressure difference, and the relative directions of the blood and dialysate flow. So there's a great historical background to hemodialysis. A physician in World War II in Nazi-occupied Holland was actually watching soldiers die because of injuries, and he thought that if there was just a way that he could remove, clear the blood, that there would be the ability to sustain these soldiers. And to his advantage, heparin had just been discovered, which is an anticoagulant, and that's huge because now you're able to pull blood out of a patient, put it back into the patient without having clotting issues that you would normally have. And so his initial prototypes, being in a war environment where he didn't have a lot of resources, were to use sausage casings for the membrane and a rotating drum setup to move the blood through the tubing. And so he had this mesh drum, he would crank it along, and he would have a bath, and he's basically just trying to move the blood through the unit and exchange by concentration gradients alone whatever was in the blood with the bath solution. So he was using washing machines for this. And you can actually see a picture here of a garden of a hospital in Kemp, Netherlands in 1944, where he's got these washing machines set up. And basically, these rotating drums, wooden drums that he's using to move the blood through. And there's just a really nice example of back-of-the-envelope calculations. Although he was a physician, I would consider what he did very engineering-like. It's saying, okay, what is the order of magnitude I need here? And what are the design specs that have to be met in order for my objective to be made? And so he was saying, I'm watching someone die from chronic uremia. If I can just remove 20 grams of urea per day from his blood, this guy might make it. So how could I do that? So he initially started out with just a bath, putting some blood in, spiking it with urea, sticking in the bath, and asking, okay, time-dependent transport, right? How long does it take for this to be removed by dialysis? So this is just membrane-based hindered diffusion transport out of it. He took that 5-minute exchange, multiplied by the length by 20, and he said, that's the length I need for an effective artificial kidney. And I love this quote because he actually went on to not only develop the first hemodialysis unit, but he was also co-inventor of the first artificial heart. So actually an amazing person, real pioneer. So I mentioned that there are a few parameters that we can control. And so while Willem Kolff really had just one type of exchange occurring where he had a bath solution and he was just trying to pump that blood through and hope that exchange was going to occur as he was pumping it through, there are different ways you can do that. You can run fluid in the same direction and have a membrane surface at which exchange is taking place. You can have it going in opposite direction. You can have orthogonal flow. And the question is, what helps you the most effectively remove spike concentration of urea from the blood? Here we're representing the blue as the dialysate solution and the pink as the blood. And so you can see there are different ways where you could control surface area for exchange. And you could look at concentration gradients that may be arising by each approach. And what I'd like to just illustrate for you here is the difference between co-current and countercurrent exchange. So let's take a minute to go through this slide because it gets the principle across. And this is just the concept that I want to share with you today. If we're going with co-current exchange, we're starting with 0 urea in the dialysate and your maximum concentration of urea in the blood at that entrance point. And as you're moving through the system and you're allowing exchange to occur across that surface area, that membrane, you're going to approach an equilibration between the two. Right? That makes sense. Even though you have convective mass transfer going in the lateral direction, you also have that diffusive mass transfer occurring through the membrane itself. And the driving potential of this exchange is the concentration gradient. So we know that that is what's pushing it across. And as you approach an equilibration, that driving potential is shrinking, right? So you're going to have less and less exchange as you reach this point here until basically they're totally the same. And then it's going to be no longer unidirectional, that molecular movement. Okay, so the best you could ever get in this co-current situation is 50% removal, right? You're going from your maximum concentration to equilibration, or depending on what your relative volumes are, you're going to reach a point in which that driving potential is minimized and you've got an equivalent amount in each chamber. An alternate situation is where you have countercurrent exchange. And this is the principle I wanted to share with you because now we've got our opposing directionality occurring. So that we have our blood starting at high at point 0, and it's moving through the system down to some new value at the end, L. You have your dialysate concentration starting at 0, but that 0 point is at the exit of the blood. And it's moving through the system, and it's getting higher and higher until it's exiting the system at your 0. Okay, so what this allows you to do is never reach equilibrium. Look at this. You've got an initial driving force, this gradient, because you have your dialysate coming in without any of your urea, and you have your concentration coming out of your system where you're at a lower value. But you have this driving force, and as you move through the tubing, you're always maintaining that differential because they're going in opposite direction. And because that gradient is what's facilitating the molecular exchange. If you have a large gradient sustained across the distance traveled, then you're going to actually reach a value for your blood that is lower than 50%. Okay? So this is a kind of a weird thing to think about, that as you're moving through, because that differential is larger, you're going to get a larger drop in your blood. So rather than going, I usually spend like an entire lecture on this topic, and rather than going through all the mathematics explaining how the molecular flow rate works and how you have these concentration gradients, using the values at each point and coming up with clearance rates and all that stuff, I just want to illustrate this visually by this concept. You may see some practice tests where we have current exchanger questions on there. You won't be responsible for current exchange on the final. But I just want to let you kind of digest that concept a little bit, because it shows up time and time again in nature. Nature has figured out how to do this. So, whales. They're beluga whales up in the Arctic Ocean. These are warm-blooded mammals, and they're in icy waters. So they have to have very effective ways to insulate against that cold temperature so that they don't cool down their body temperature just through the thermal exchange across their skin. So the way they do that is they actually have a really different sort of insulation and capillary arrangement of their blood vessels than other sort of land mammals. And the way they do that is they basically try to minimize the escaping heat by warming up the returning blood from the surface to the core of the body through this countercurrent heat exchange. So they're able to maximize the thermal exchange across here by this countercurrent mechanism. Whereas if they were just having this formation here, they would have much more heat exchanging in terms of what the cool value would be returning to the body. So that's one way in which this arrangement of countercurrent flow is useful. This is also seen with birds in standing water. The way they orient their veins and arteries is they actually have them side by side, so that while they've got sort of this dispersed capillary structure in their feet, when they get back to their legs, they're going to want to have these right adjacent to one another so that you have thermal exchange across here. And again, that's to minimize having really cold temperature blood returning back to the core of the body. If you can maximize the thermal exchange in a given distance, here the distance is constrained by the size of the legs, then you can actually warm up things faster for a given flow rate. And so that's how birds do that. This is also true for mass transfer and in fish. So if you want to think about how fish extract oxygen from water, if you think, I'd never, until I thought about sort of these countercurrent exchange things, I never really thought about how gills work in fish. But if you think about it, you have a certain perfusion of oxygen in your seawater, right? And so you can have your maximum oxygen content in the water, and then if you're just flowing blood across the water alone and allowing diffusion to take place, the maximum you could get out under the co-current situation would be like 50% exchange. So for the gills to be more efficient for respiration, instead what they do is they have opposing directions. So as they're swimming through the water, the water stream is coming one way, and they actually have their capillaries oriented the other way in terms of their flow. And in doing so, you're going to have a higher diffusion because you're maintaining that gradient throughout with the countercurrent exchange. And as a result, equilibrium is not reached, and you get almost 90% exchange at the end point of the capillaries, which is great because, you know, as you're moving through the water, you want to get as much oxygen out of it as possible. So that then is the end of countercurrent exchange. Oh, just to let you know, heat follows the same principles as the hemodialysis, but you can have actually phase change occur. So this is possible with evaporators and condensers. And in doing so, the directionality of one of your flows doesn't matter because it's just turning into vapor or steam, or it's cooling down. But that's just a special circumstance for heat exchange. So at least you guys know about countercurrent and why this is such a useful way of facilitating mass or heat transfer. All right, so Friday, we're back in here. No flip session. I'll send out a Piazza reminder. Come prepared to review the whole course. We'll clear up any concepts you have. All right?